Greetings students, as you've gone through the lectures corresponding to magnetic effects of current and magnetism, we'll now try to work out some of the basic problems which we come across in competitive exams of your interest. So let's start off with the first question. First question states, a charged particle moving in uniform magnetic field and loses 4% of its kinetic energy. The radius of curvature of its path changes by, we know that the radius of curvature R is equal to mv by bq. We now somehow have to establish a relation between the radius of curvature R and the kinetic energy Ke. So squaring this expression, R square V square Q square is equal to M square V square. Shuffling the different terms over here, we can end up getting the relation between the radius of curvature and the kinetic energy, which is equal to R BQ is equal to root over 2m times the kinetic energy. This clearly states that R, that is the radius of curvature, is proportional to the root over kinetic energy. Let R dash be the new radius of curvature which we are looking for, divided by the old radius of curvature. This is equal to root over Ke dash, the new kinetic energy, divided by root over Ke, the old kinetic energy. With the given information that there is being a loss of 4% in the kinetic energy, we can state that Ke dash, the new kinetic energy, is equal to 0.96 times the old kinetic energy. Using this information over here, I can write that R dash, that is the new radius of curvature, is equal to root over 0.96 times the old radius of curvature, which comes out to be 0.98 of the old radius of curvature. This specifically tells me that there has been a loss of 2% in the radius of curvature. So A, 2% is the correct answer. So moving on to the next question. The Earth's magnetic field at a certain point is 0.7 gauss. This field is to be annulled by magnetic field at a center of a circular conducting loop 5 cm in radius. The required current is about, we know that the magnetic field at the center of a circular conducting loop is equal to mu naught I, the current in the loop, divided by 2R. This is equal to the magnetic field of Earth, that is 0.7 into 10 to the power minus 4 Tesla. Substituting the values of mu naught and R, we can end up getting the value of the desired current. So I is equal to 2 into 0.05 meters into 0.7 into 10 to the power minus 4 divided by 4 pi into 10 to the power minus 7. With this, we end up getting the value of current to be 5.56 ampere, which is almost equal to 5.6 ampere. So B, 5.6 ampere is the correct answer. So let's try out the next problem. Two charged particles, each of mass m and charge q, are projected in a uniform magnetic field B with same speed as such planes of motion of particles are perpendicular to magnetic field B. Then the following statements are given. A. They move on circular path of same radii. We know that the radius of curvature of a particle moving inside a magnetic field is given by R is equal to mv by bq. We know that they have the same mass, speed and the charge, and the magnetic field is common to both these charges, hence the radius of curvature for both these particles will be same. Next statement, the magnetic forces on them are same to each other. We know that the magnetic force F is equal to QVB. Again, the charge and the speed is one and the same for the both particles, and B, magnetic field, is common both of the particles. Hence, the magnetic force is same for both the particles. So B is also a correct statement. C. The kinetic energies of particles are same to each other. We know that the magnetic field doesn't do any work on a particle traversing inside a magnetic field. So there is no change in the kinetic energy of that particle. So Ke is equal to half mv square. We know that the mass and the speed of both the particles are same. So the kinetic energies of both the particles remain unchanged and they are equal. So C is also correct. Hence D, that is all of the above statements are correct. So let's move on to the fourth question. Fourth question states, a charged particle enters a region of non-uniform field and eventually comes out of it. As it emerges, its A. Speed is greater as compared to the speed at entry point. We know that the magnetic field doesn't do any work, so there is no change in the kinetic energy of the particle. So the initial speed must be equal to the final speed. Hence, this is a false statement. B. Velocity remains unchanged. It's not necessary that the velocity remains unchanged. Why? Because there can be a change in the direction of the motion. Let's say the particle is entering like this and the particle may go out like this. So there can be a change in the direction of the motion of the particle, but the speed remains unchanged. Hence, this is also a false statement. C. Velocity may change, but speed remain unchanged. Now, this is quite feasible. That is, there might be a case that the direction does change, but we know for the fact that speed is not going to change. So this is a correct statement. D. Speed cannot be estimated as data is insufficient. We don't need to give any statement about speed, that is what is the magnitude of it, or what is changing or not, it's increasing or decreasing, but we just need to give the statement that whether the speed remains unchanged or it's changing. So we know that the speed remains unchanged. So again, this does not satisfy to our cause. So C, velocity may change but speed remain unchanged. That's the correct option. Moving on to the fifth question. A long wire carries a current of 20 ampere along the axis of solenoid. The field due to the solenoid is 4 millitesla. The resultant field at a point 3 mm from the solenoid axis is, so let's say this is my solenoid and the axis corresponding to the solenoid is this, where I have a long wire which is carrying a current of 20 ampere. We need to find field, let's say 3 mm from the axis. So we know that the field due to solenoid is in this direction and has a magnitude of 4 millitesla. The field due to the wire carrying the current along the axis of the solenoid will have a field which is perpendicular to it. So the direction corresponding to it will be like this. It's going inside, or let's say it's going outside the page, coming towards me. So the resultant field will be 4 millitesla plus field due to the wire. So the resultant field is a combination of 4 millitesla due to the solenoid and the field due to the wire. Now we need to find out what's the value of the field due to the wire. We know that for the wire, B is equal to mu naught I by 2 pi d, d being the distance of separation. So B is equal to 4 pi into 10 to the power minus 7, I is given to be 20 ampere, divided by 2 pi, d is 3 mm, so it's 3 into 10 to the power minus 3. This comes out to be 1.33 millitesla. So the resultant field will be somehow like this, 4 millitesla, 1.33 millitesla, and here's the resultant field. So it comes out to be 4 square plus 1.33 square root over, which has a value of 4.2 millitesla. So B, 4.2 millitesla, is the correct answer. So let's move on to the next question. AB and CD are smooth parallel rails separated by a distance L and inclined to a horizontal at an angle theta. An uniform magnetic field of magnitude B directed vertically downward exists in the region. EF is a conductor of mass M carrying a current I. For EF to be in equilibrium, the following conditions are given. So for EF to be in equilibrium, I need to have a force which cancels out this mg sine theta. So I need to have an equal and opposite force in this direction due to the magnetic field present over there interacting with the current, which cancel out my mg sine theta. So this is FB. So force due to the magnetic field is equal to mg sine theta, because that's what we actually need for EF to be in equilibrium. Now, the force due to the magnetic field is, as we know, is B cos theta IL. We are considering B cos theta over here because B is at a certain angle with the current flowing in EF conductor. So B has to be perpendicular to the current flowing. So B cos theta is the component of the magnetic field which is perpendicular to the current flowing in the conductor EF. So B cos theta IL is equal to mg sin theta. So from here we got the condition that BIL is equal to mg tan theta. Hence B is the correct answer. BIL is equal to mg tan theta. So now let's try out a different question. A conductor ABCDEF with each side of length L is bent as shown. It is carrying a current I in uniform magnetic induction field B parallel to the positive Y direction. The force experienced by the wire is, so the current flows like this from F to E to D to C to B then to A. Now we need to find out the net force which is being experienced by the wire ABCDEF. Now we know that these ends of the wire will feel equal and opposite force. So the net force experienced due to AB and EF will be 0. The same goes for the branch BC and ED. Net force again experienced by these two branches are equal and opposite and hence a 0 force. Now for the branch CD, I have a current moving in this direction and I have magnetic field along positive y-axis. So I need to just take a cross product of I cross B. So I will get a force in this direction, that is in positive Z direction. So BIL in the positive Z direction, that's the correct answer. So let's try out the next problem. The next problem states, a particle of charge q and mass m moves in a circular orbit of radius of r with angular velocity omega. The ratio of the magnitude of its magnetic moment to its angular momentum depends upon. We know that the magnetic moment m is given by the current which is flowing in the loop I multiplied by the area. Current in this particular circular loop is equal to q, the charge flowing, and the time it takes to cover one revolution, that is 2 pi by omega, multiplied by pi r square. So my magnetic moment comes out to be q omega r square divided by 2. Now angular momentum in the other hand is equal to m omega r square. So if I take the ratio of the magnetic moment and the angular momentum, it comes out to be q by 2m. So the ratio m by L clearly depends upon two physical parameters, the charge and the mass. So C, Q and M is the correct option. So let's try a next problem. A charged particle is projected in a plane perpendicular to a uniform magnetic field. The area bounded by the path described by the particle is proportional to. We know that the radius of curvature r is equal to mv by bq. So the area covered by it is equal to pi r square, which in turn is equal to pi times m square v square divided by b square q square. In this particular expression, I multiply 2 in the numerator and divide by 2 in the denominator. So the area comes out to be 2 pi m times the kinetic energy divided by b square q square. This clearly comes out with the statement that area is directly proportional to the kinetic energy. Hence C over here, that the kinetic energy is directly proportional to the area bounded by the path, is the correct answer. So let's try the next problem. An electron accelerated by 200 volt enters a magnetic field. If its velocity is 8.4 into 10 to the power 6 meter per second, then for E by m, what will be the value? We know that EV is the accelerating potential or the energy which is given to the electron. This equals to the gain in kinetic energy. So it's starting from the rest. So let's say it gains this much amount of kinetic energy resulting into the speed. So E by m actually comes out to be V square, that is speed square, divided by 2 times the voltage that is being supplied. So if we substitute the value of V over here, that is speed, and the voltage, we will see that E by m actually comes out to be 1.75 into 10 to the power 11 coulomb per kilogram. Hence B over here is the correct answer. So let's try the next problem. It states two particles accelerated with same voltage enter a uniform magnetic field perpendicularly. The radius, if the circular parts are r1 and r2, the charge on the particles is same. The ratio of m1, m2 is, we know that the radius of curvature r is equal to mv by bq. And it's being accelerated with the same potential. This is the information which is given in the question. So EV is equal to half mv square. So with this, we can find out the speed. So speed is equal to 2e times the voltage divided by m. So this is the speed with which the particle is entering into the magnetic field. Substituting the value of the speed over here, we end up getting this: r equals to m root over 2ev by m multiplied by 1 by bq, which in turn is equal to r 2ev m divided by bq. This comes out with a statement that r, that is the radius of curvature, is proportional to root over m. So m1 by m2 is basically equal to r1 square divided by r2 square. Hence d, that is m1 by m2, is equal to r1 square divided by r2 square. That's the correct answer. So let's try the next question. Length of two wires is 1 meter and the distance between the wires is 0.5 meter. If 1 ampere current is passed in the wires, force per unit length between the wires is, we know that the force per unit length in between the two wires is equal to mu naught I1 I2 divided by 2 pi d. That's the separation between them. It's given that the length is 1 meter and the distance between the wire is 0.5 and the current is 1 ampere in each of them. So it's basically 4 pi into 10 to the power minus 7 into 1 into 1 divided by 2 pi into 0.5. So this comes out with the answer that 4 into 10 to the power minus 7 Newton per meter. That's the force per unit length. Hence A, 4 into 10 to the power 7 Newton per meter. That's the correct answer. So let's try the next question. It states, specific charge on a proton is 9.6 into 10 to the power 7 coulomb per kilogram. A proton is moving in a magnetic field of 1 Tesla in circular path of 0.5 meter radius. The energy of proton in mega electron volt is, now we know that the radius r is equal to mv by bq. It's given that the specific charge of the proton, so it actually means that E by m, that's the value which is being given over here. So we'll just take the terms of m by q to one side. So r, we call this as c times b is equal to my speed. Using this expression, I need to calculate the speed, or let's say correspondingly the energy of the proton in mega electron volt. So half mv square is the kinetic energy of the proton, which in turn is equal to half m rcb square. So for proton, I know it's 1.6 into 10 to the power minus 27 kilogram. Substituting the values of the radius, that is, it's given to be 0.5, b to be 1, c to be 9.6 into 10 to the power 7 square, we end up getting the value of the kinetic energy. We need to multiply this or divide this by 1.6 into 10 to the power minus 19 to get the energy in electron volt. So this comes out to be 12.02 mega electron volt. Hence B is the correct answer. So let's try the next question. It states the magnetic field due to a straight current carrying wire is 10 to the power minus 5 Tesla at a distance of 10 centimeter. The current in the wire is, we know that due to a straight current carrying wire, the magnetic field is given to be mu naught I divided by 2 pi d. We need to find out the current, so the current is equal to 2 pi d times the magnetic field divided by mu naught. So substituting the values of all the parameters which we have with us, so it's 2 pi times d is given to be 10 centimeters, so it's 0.1. B is given to be 10 to the power minus 5. Mu naught is 4 pi into 10 to the power minus 7. That's my current. So current comes out to be 5 ampere. So B, 5 ampere is the correct answer. So let's try out the next question. An electron of mass Me and a proton of mass Mp are injected into a uniform magnetic field at right angles to the direction of the field with equal velocity. The ratio of the radii of their orbits Re by Rp is equal to, we know that the R, that the radius of the curvature, is equal to mv by bq. So if we want to find out the radius of curvature of both the electron and the proton, so Re by Rp is equal to Me. So it's given that they are injected into uniform magnetic field at right angles to the direction of the field with equal velocity. So their speeds are same. So V gets cancelled out when we're talking about the ratios, and B also gets cancelled out because they are in the same region. Same goes for Q because they have the same charge, that is E. So it's basically Me by Mp. So Re by Rp is equal to Me by Mp. Hence D is the correct answer, Me by Mp. Moving on. Electron of mass M, charge E is traveling with a speed along a circular path of radius r at right angles to uniform magnetic field B. If the speed of the electron is double and the magnetic field is half, the resulting path would have radius. So R is equal to mv by bq. It's given that the magnetic field is being half. So let's say B dash is the new magnetic field and I have this equal to B by 2, that is half of my initial magnetic field. And the speed is being doubled, so V dash is 2V, 2 times my initial velocity. So R dash is equal to M multiplied by 2V divided by B by 2 times Q. So R dash comes out to be 4 mv by bq, which is equal to R dash is equal to 4 times my initial radius of curvature. So D R dash is equal to 4R, that is the new radius is 4 times my initial radius. That's the correct answer. So let's try out the next question. The strength of the magnetic field at a point distance r near a long straight current carrying wire is B. The field at a distance r by 2 will be. So the magnetic field due to a long straight current carrying wire is given to be mu naught I, that is the current inside the wire, divided by 2 pi d. It's given that the distance is being decreased by half. So let's say B dash is equal to mu naught I divided by 2 pi r dash, where r dash is equal to r by 2. So substituting the value of r dash over here, I end up getting 2 times mu naught I divided by 2 pi r, which is equal to my initial magnetic field. So B dash is equal to 2 times my initial magnetic field. So D, that is B dash is equal to 2B, is the correct answer. So let's try out the next question. Here we have been asked to find out the dimension of the magnetic field. In this particular type of question, we need to find out the relation between the already physical parameters which we know of to the parameters which is being asked. For example, I know a relation which relates magnetic field to the force, and I'm very comfortable with the force, that is the dimensions of the force. So F is equal to QVB. So dimension of the magnetic field is equal to force, dimension of the force divided by the dimension of charge divided by the dimension of the velocity. This is equal to mLt minus 2 QLt minus 1. This comes out to be mL0 t minus 1 q minus 1. Hence this B mL0 t minus 1 q minus 1 is the correct answer. That is, the dimension of the magnetic field is this. So let's move on to the next question. It says that the sensitivity of a moving coil galvanometer depends on. We know that the sensitivity of a moving coil galvanometer is given by NAB by K. So if I'm increasing the number of terms, area or the magnetic field, there is no change in the sensitivity of the moving coil galvanometer. So the parameters here given are angle of deflection, Earth's magnetic field, moment of inertia of the coil. These all parameters never affect the sensitivity of the moving coil galvanometer. Hence D, none of the above is the correct answer. Moving on. A straight wire carrying a current of 10 ampere is bent into a semicircular area of radius 5 centimeter. The magnetic field, or let's say the magnetic field at the center is, so we are being asked to find out the magnetic field at the center where it's carrying a current of 10 ampere and the radius is 5 centimeter. For a semicircular arc, magnetic field is given as mu naught I divided by 4R, which is just the half of a circular conducting loop. So magnetic field comes out to be 4 pi into 10 to the power minus 7 into 10 multiplied, or let's say divided by 4 into 0.05. So the magnetic field comes out to be 6.28 into 10 to the power minus 5 Tesla, and C, 6.28 into 10 to the power minus 5 Tesla is the correct answer. Moving on. With a resistance R connected in series with a galvanometer of a resistance 100 ohm, if acts as a voltmeter of range 0 to V volt, to double the range, a resistance of 1000 ohm is to be connected in series with R. Then the value of R in ohm is, so it's given that I have a galvanometer whose resistance is 100 ohm, and in that I am connecting a resistor whose resistance is R, such that it gets converted to a voltmeter which can measure up to V volt. Now I want to convert it into a new voltmeter. For that, I have 100 ohm of the galvanometer and the resistance R, and also I am attaching an extra 1000 ohm such that this becomes a voltmeter which can measure up to 2V. So 2V is equal to Ig, that is the current inside the galvanometer, is equal to 1100 plus R, and V is equal to the same current which flows through the galvanometer, and it's equal to R plus 100. If I just take the ratios of these two, then 2 is equal to 1100 plus R divided by 100 plus R. Just calculating the value of R from this particular equation, we found out that the R is equal to 900 ohm. So we need to connect a resistor of 900 ohm in series to convert a galvanometer into voltmeter of V range, and if we connect to the same setup an extra 1000 ohm, we can just double its measuring capability. So C, 900 ohm is the correct answer. Moving on to the next question. It says a galvanometer is of 25 ohm. Resistance can read a maximum current of 6 milliampere. It can be used as voltmeter to measure maximum of 6 volt by connecting a resistor to the galvanometer. Identify the correct choice on the given answer. So it's given that there is a galvanometer whose resistance is 25 ohm and it can carry up to a current of 6 milliampere. I'm converting this galvanometer into a voltmeter by obviously connecting a resistance in series of value R, and it still can carry up to 6 milliampere. The reading it can give is up to 6 volt. So 6 is equal to, the 6 volt is equal to 6 milliampere times 25 ohm plus R ohm. So this comes out to be 1000 is equal to 25 plus R, or R is equal to 975 ohm. Hence C, 975 ohm in series is the resistance which you need to convert a galvanometer into a voltmeter with a maximum reading possible of 6 volt. Moving on. If an electron revolves in a path of a circle of radius of 0.5 into 10 to the power minus 10 meter at a frequency of 5 into 10 to the power 15 cycles per second, the electric current in the circle is, the charge of the electron is given, that is 1.6 into 10 to the power minus 19 coulomb. So when a particle is moving in a loop, having a charge q, the current in that particular loop is basically the charge it carries divided by the time it takes to convert one cycle. So if you look closely over here, charge q multiplied by 1 by t is nothing else than q, the charge multiplied by its frequency. So the current over here is simply 1.6 into 10 to the power minus 19 coulomb multiplied by 5 into 10 to the power 15 cycles per second. So this comes out to be 0.8 milliampere. That is the current in this particular loop. So B, 0.8 milliampere is the correct answer. Moving on. Two long parallel copper wires carrying currents in the opposite direction of 5 ampere each. If the wires are separated by a distance of 0.5 meter, then the force between the wires is, so it's given that the two coppers wire are carrying current in an opposite direction. So they are obviously not attractive in nature. We know about that. It's either this or either this. The force per unit length F by L is given to be mu naught I1 I2 divided by 2 pi d. Substituting the values of the different parameters over here, we will end up getting the value of the force per unit length. So it's 4 pi into 10 to the power minus 7 multiplied by 25 divided by 2 pi multiplied by 0.5. So this comes out to be 10 to the power minus 5 Newton per meter. Hence B, 10 to the 5 minus 5 Newton per meter and repulsive in nature is the correct answer. Moving on. An electron beam is allowed to pass normally through magnetic and electric field which are mutually perpendicular. When the magnetic field induction and the electric field strength are 0.0004 Weber per meter square and 3000 volt per meter respectively, the beam suffers no deflection. Then the velocity of electron is, in this particular situation, it clearly states out that the force due to the magnetic field is being properly balanced or cancelled out by the force due to electric field. Hence, QVB is equal to small e times capital E. This is the magnetic force, this is the electric force. Now, VB is equal to the electric field. So, velocity or the speed comes out to be electric field divided by the magnetic field. So, it's equal to 3000 divided by 0.0004, which comes out to be 7.5 into 10 to the power 6 meter per second. Hence, A, 7.5 into 10 to the power 6 meter per second is the correct answer. Coming to the new set of problem, that is here we will be dealing with comprehension. To tell you more about comprehension, comprehension is basically a setup which will be given to you in front of you actually in competitive exam, and it's very popular in competitive exams. So this setup or any setup will be given to you, and the corresponding data for this setup or any setup will be given to you. And based on the data and the setup, various set of questions will be asked on it. Now the crucial part about comprehension is to get hold of the first question. It gives you the confidence that you have completely understood the setup and the data corresponding to it, and it preps you for the coming 2 or 3 questions. And obviously it's very scoring because it's related to one situation only. So make sure you do get hold of this type of problem, that is how to deal with comprehensions. So let's study this comprehension. A wire of resistance R in the form of semicircle lies on the top of a smooth table. A uniform magnetic field B is confined in the region as shown. So B is over here, it's confined to this particular line. No B below that, and there is a definite B above it. The ends of the semicircle are attached to the spring C and D. So these are my 2 springs C and D, whose other ends are fixed. If R the radius of the semicircle and K is the force constant of each spring. So this is the total setup, that is, this is R magnetic field is confined in this space, this is the spring, and this is the power source with EMF E. Based on this, I will be asked a set of questions. So let's try out the set of questions regarding this comprehension. It's given, you need to find out the net force constant of the spring. So current is flowing in this direction, magnetic field is into the page. So it means this will this semicircular arc will feel a force in this direction. So the spring will get stretched. And at some point, this magnetic force will be balanced by the spring force. At that particular point, F is equal to Kx extension in the C spring plus Kx extension in the D spring. So F is equal to 2Kx, where the magnetic force will actually feel that it's being withheld by a spring of effective spring constant 2K. Hence, B, 2K is the correct answer. Moving on. Force applied on the semicircular wire of radius r due to the current. So force in general, it's given like this. F is equal to I dl vector cross B. In this particular case, my I is constant, so the current goes out of the integral sign. So it becomes dl cross B. B over here is also constant. So at the end of the day, I'm basically summing up small vectors of dl magnitude starting from this point and ending to this point. So it's basically summing up different vectors, small vectors along a semicircle. So in the end, it comes out to be LR, that is the resultant vector, the magnitude of resultant vector multiplied by the magnitude of the magnetic field is equal to the force which the semicircle feels. So this is equal to the resultant of all these small vectors is basically this vector, which has a magnitude of twice the radius. So I times 2r times B is the force which you feel. So it's 2I small r B is the magnitude of the force which the semicircular wire feels. So D 2IBR is the correct answer. Moving on. What will be the extension X of the spring? So we just found out that the force was equal to 2IBR. We just need to express the current in terms of EMF and the resistance of the semicircle wire. So it's 2EB small r divided by capital R. That's the force. This force is being properly balanced by the extension in the spring of C and of D. So Kx plus Kx. So 2EB small r divided by capital R is equal to 2Kx, implies X is equal to EB small r divided by K times capital R. Hence C EB small r divided by K capital R is the correct answer. Moving on to the 29th question, it states that a coil in the shape of an equilateral triangle of side 0.02 meter is suspended from vertex such that it is hanging in a vertical plane between the pole pieces of permanent magnet, producing an horizontal magnetic field of 5 into 10 to the power minus 2 Tesla. Find the couple acting on the coil when the current of 0.1 ampere is passed through it and the magnetic field is parallel to its plate. Let us take up this setup, that is, this is an equilateral triangle and the current is flowing like this of magnitude 0.1 ampere and the side is given to be 0.02 meters and a magnetic field is 5 into 10 to the power minus 2 Tesla that is being set up. We need to find out the couple, that is the torque acting in this particular setup. This is basically M cross B, the magnitude of the magnetic moment and the magnetic field. So the torque or the couple is basically equal to, substituting the different values of it, the current in the circuit is 0.1, the area of the equilateral triangle is root 3 by 4 a square, a being 0.02 meter and B is also given in 5 into 10 to the power minus 2 Tesla. If you substitute all these values, which we have done already over here, we found that the value of the moment is 8.86 into 10 to the power minus 7 Newton meter. Hence, A is the correct answer. So let's move on to the last question. It says we need to find out the dimension of magnetic permeability. In order to deal these kind of problems, you first need to have a relation which relates to the quantity whose dimension you need to find out to the quantities whose dimension you already know of. For example, force per unit length is equal to mu naught I1 I2 divided by 2 pi d. This is corresponding to force between two straight conducting wires which are carrying currents. So We know the dimension of force, we don't know the dimensions of the length, the separation, we also know the dimensions of the current. Hence, force basically is now equal to mu naught I square 2 pi dl, or the dimension of force is equal to the dimension of mu naught equals to dimension of I square. So ml t minus 2 is equal to the dimension of mu naught times the dimension of q by t square. So this comes out to be ml t0 q minus 2 is equal to the dimension of permeability. Hence D is the correct answer. That is ml t0 q minus 2 is the dimension of magnetic permeability. So I guess you have learned quite a lot about the application part of the concepts which you studied in the chapter of magnetic effects of current and magnetism through these set of questions. If you have any other doubts related to the concept or the application part of it, you can post your doubts on the discussion forum. Till then, bye bye and take care.